Okay, so this is part two of topic one, part three. We'll pick up on slide 48. So we've really already seen what faceting does. We know that when you facet in a graph, you need a variable, a categorical variable that has data on it, where you're going to create a graph for each set of data corresponding to each level of a categorical variable. We also call those, factors in R. So in this case, when we look at this ggplot, for example, we have our first statement, our data, we have our aesthetic, then we have our geom, and then we add another layer that says, now I want to see that by each level of the class variable. And the levels of the class variable are compact, midsize, SUV, two-seater, minivan, pickup, and subcompact. So I'll let you run this line on your own. But when we look at the graph, we can see that we get some are interesting, some are not so interesting. And a large reason why some of these are not that interesting is because they don't have much data. But you can see in the two-seater cars where they when we have a large engine, our mileage tends to be lower than most of the other cars. If a minivan, it's interesting, the minivan doesn't have as large of an engine as a two-seater, but again, its mileage, fuel economy, its highway fuel economy is lower. SUV, it looks exactly the way we think it should look, and then compact and pickup. So when we look at these types of graphs, they should be telling us things that actually make sense. And sometimes they won't make sense because you might not understand the data that well. And so you might need a data expert working with you to help you look at these relationships to see if they make any sense. So right off the bat, we have a homework problem. And so here you're going to try to see what happens if you try to facet a continuous variable like highway. And then what about cylinder? And then what's the key difference here? And using faceted, you want to explore the three-way relationship between fuel economy, engine size, and number of cylinders. And answer the question, how does faceting by number of cylinders change your assessment of the relationship between engine size and fuel economy? So that should be also telling you something that you can opine on, and basically it'll be your observations of the graph. Then what arguments can you use to control how many rows and columns appear in your output? That's just a fact. You have to read the documentation to understand that. And then what does the scales argument do for the facet wrap, and when might you use it? So again, I'm asking you to look at the documentation to address questions 3 and 4. We have other functions, just like we did in base R. We have a smooth function that will give you a nice smooth line. We did this with AB line in the last in base R. We have the box plot function, histogram, the frequency polygon, a bar chart, a path chart, and a line. So some of these are new, but we'll see exactly how each one of these works, especially the path one, because that one is probably very new to most of you. So if we want a smooth point, all we're doing is saying, can you please put a curve of best fit that runs through all these points? And when we say a curve of best fit, we typically mean, in simple terms, draw me a curve that's as close as possible to all these points. And we could make the curve really close to every point just by connecting the dots, right? Then the curve is exactly close to every point. But that's really not a good prediction curve, because it's really built to the exact orientation of the data. And when that happens, we say that our model is overfit. We want a curve that's generally true, for most of the data, and we talk about how well models generalize to unseen data. So we build it on one set of data, and then we test it on another set of data and see how well it generalizes. And so we're really looking for something that doesn't have too much wiggle in it, and it kind of gives us an average fit through all the points. And these gray bars that you're seeing, this gray area around the curve, that refers to the standard error. And what's interesting is that when you have more points, your standard error is smaller than when you have a lot of points, because there wasn't much to go on to build the data in this region. So it gave you kind of the widest range possible of being able to make a guess as to what the point would be in that region. But where you see the gray area smaller and tighter to the line, that means we had enough data to get pretty confident to figure out when we could be within a 95% confidence of picking a number in the right range. These other functions, the GeoSmooth functions, we have a low S function, we have a low S function, and we have a GAM, GAM, and a cubic polynomial. So the low S function stands for locally weighted scatter plot smoothing. And again, this is just for your information. We're not going to do much with these curves in this class. But I want you to really just take a look at how the different red lines fit the data. You can see in some points, some of the data, the red line doesn't fit very well, like in the low S, the upper right left graph. Towards the endpoints, it doesn't really fit very well, but the low S has a much better fit on that lower end of the graph. And, different types of polynomials will give you different types of fit. And they all use a little bit different methodology. But the one to really pay attention to here is the GAM function, that stands for Generalized Additive Model. And that's basically, we like to say that this type of curve, it's really good when you have very wiggly data. So when you think wiggly data, you want to think GAMs, because they use splines to kind of do a piecewise fit on your data. So we can make a curve very wiggly if we want. We can get kind of a curve that appears to go through, most of the dots are snakes through the shape a lot better. And we can do that with the span function. So in the GeoSmooth, this span parameter, it ranges from 0 to exceedingly wiggly to 1, which is not very wiggly. And we can see when we have a span of 2, we get the graph on the left. But again, all this wiggliness is not really represent a good fit of the data, because it doesn't generalize very well. So for example, if I picked a point around this region of this curve, and let's say my point was up here, well, this curve is going to predict it as a very small number, much lower than it actually is. But if I get something that's closer to like the means of each one of these vertical bars, which is basically the kind of fit, the way we try to fit data, is we look at each one of these and try to fit, the mean, then we're still going to have some error, but we won't have as much error as we would in this wiggly case. Whereas in the second case, this one is fit more to the mean about each one of these vertical sets of points, and it looks much smoother. It's a much prettier curve. We say it's generalized as well. We wouldn't have as much error if we go to that same spot and pick the point. It would be much closer to this line than it would have been on our other graph. The GAM function, like I said before, it fits using splines, and we're not going to really talk much about the theory. behind splines. But this GAMs are used a lot in modeling in the real world, mainly because when you use a spline is considered a perfect cubic polynomial. So people like to work with splines, plus you can fit them piecewise, and the derivative will still exist when you do at those connections. So we like to, a lot of people like to model with GAMs. Then if we can have a linear fit, well, this linear fit clearly doesn't do a very good job at all of predicting the extremes. I mean, here's at number 7, this point's way up here, but the line is predicting that it's way down there. So definitely a linear model doesn't fit, but it doesn't hurt to try every type of model and fit to your data. In fact, there are software packages that will run your data set through pretty much every kind of model you can think of. And then you're left with, and then it rank orders the models to see which one has the best fit. And, there is something educational about that too. But, typically we try to use our exploratory data analysis to help us understand what the right distribution is that's going to fit our data. And then we have something called, more of a robust linear model. And, I really don't see a big difference between the RLM and the LM. They look pretty similar to me. But, we still see that this, even with the RLM, it's not a good fit. Give me 1 second. Okay. So something that happens a lot when we have a lot of discrete data is that several observations can have the same value. And when we graph them, we really can't get a sense for the density of the data because they're stacked on top of each other, right? If this was a 3-dimensional graph, we could turn it sideways and look at the heights of each stack, but we can't do that in a 2-dimensional graph, which is fine. So what we want to do is we want to analyze this a little bit differently than just looking at the raw scatter plots. Because this is a situation where we have overplotting, where one point gets plot over the next, over the same point over and over again. And if we want to get a sense for how much data is at along each one of these values of drivetrain, then we need to, we can do something, we can look at a box plot, for example. Box plots work really well. They give us information about the distribution. But R also has this thing called jittering, where you just move every point a little bit away from each other so that they come off that stack and you get to see like how much data is concentrated for a given value. And then there's something called violin plots. And when we look at violin plots, you'll see why they're called violin plots. But again, all of these techniques are really intended to deal with overplotting so that we can get a good sense of what the distribution of the data is, how much is there, how dense it is for every level of every variable. So in this first case, we can see this ggplot with highway as a function of drivetrain. When we scatter, we get a real nice look at how much data is really concentrated for 4-wheel, front wheel, and rear wheel drive vehicles. If we use a box plot, and I should say I'm not a big fan of jittering. I think you shouldn't do your data is your data, and you shouldn't alter it. And that's what jittering does. It's altering it because it's adding something to its X or Y value so that you get a greater sense for how much data you have. But there are other techniques that give you that information without you having to manipulate or change your data in some way. And that's a box plot. When we look at a box plot, I mean, we can clearly see the distribution. We have the median and the four. We can see that four-wheel drives and rear-wheel drive cars, they're kind of similar. Their box plots are overlapping. So that means in terms of highway fuel economy, there's really not that big a difference between a four-wheel car, a four-wheel drive car, and a rear-wheel drive car. And I think probably most people know that. So the data should actually bear us out. Now, front-wheel drive car is different. That gets better fuel economy, and I think people also know that as well. But the box plot is showing you that the boxes is not overlapping with the four-wheel cars and the rear-wheel drive cars. So that's saying, this graph is telling me immediately that front-wheel drive cars are statistically significantly different from four-wheel drive and rear-wheel drive cars when it comes to highway mileage. And again, that would say, if I were building a model, I might say, well, since the four wheels and the rear wheels are not that different, I can just put them into one bucket and model them together. And so I'll have two buckets. My front wheel drive will be one bucket, and then my four and my rear wheel drive cars will be in another bucket. And that helps simplify your model. This next plot is your violin plot, and you can kind of see why they're called violin plots, especially if you look at the four-wheel drive. That looks more like a violin than some of the other ones, but they generally have the same characteristics of the shape of a violin. We have histograms, again, where we can, count the number of cars that get highway mileage, and we can then, you can't really tell which car is which in this case, but you can get some spikes along the way. So, this is just a count of cars in each one of these buckets. And then we can do the same thing. Instead of having this block look, we can use the frequency polygram function or polygon function. And all that does is, if we go back to the histogram function, it takes the midpoint of the height of every bar and it connects them. So we go from here to here, up to here, then up to here, then we connect this point and that point, this point down and this one. We just do that through the whole thing. So this is just really connecting the dots, where the dots are the midpoint of each bar height. So we take the coordinates for that position, and that's what we're plotting. And you can see that's exactly what we did here. We went up, then down, a little bit up, then way up, then down back, a little bit more, etc. You can compare the graphs and see that those are equal. And we just used like bins equal 30. So here again, you can, by default, it will set the number of bins equal to 30, but you can actually change that. So you don't have to, you can have more bins or less bins. But again, I think, like I said last time, when you start playing around with how many bins you have, you get more, you can become so granular that the information is not that useful, or you can become so aggregated that, again, the data is not that useful. So you're trying to find kind of that sweet spot that helps you scoop up all of the bin that have very little data, because you want credible data. So you can see out here beyond 40, there's not much data here. So you might want to group, data from around 32 on and put them into one bin. And then there are other places where you could do some strategic grouping as well. But you'll get you'll do that a lot when you start, building models in the real world. And we just talked about this binning. So binning is really helpful to help you make sure that you're modeling data that has a credible number of observations. So this is what the difference is, and I was talking about that before. If you have a bin width of 2.5 versus a bin width of 1, you can see this looks more aggregated on the left than it does on the right. And then the question is that helpful or is it hurtful when you're trying to do the modeling? And typically what people do is they say, well, let me try it both ways and see how the performance of my model is impacted if I get a model that's more statistically significant or one that's less, that's depending on the bin. So they let the model performance help be a deciding factor for how you group your data. So we also have the density function, and these densities can be, I mean, I think they're fine. I don't think they're that difficult to interpret, but they definitely are, some of the computations are more complex. And, they may make assumptions that are not true for all the data, and that's that the underlying distribution is continuous, unbounded, and smooth. But here you can see this is the code. This code is what builds this graph. And what's really nice about, we have 3 sets of data where we create some random numbers from a normal distribution with different means. So here's the first one with a random 10,000 observations from a random normal with a mean of 0, then 10,000 with a mean of 2, and 10,000 with a mean of 5. And in all cases, this assumes that the standard deviation is 1. So you can see we get these 3 sets of data, and we want to see how does the shape of that data change significantly based off of the transparency that we see and the different means that we have. So this is a really good exercise because I can now compare 3 graphs on 3 sets of data on the same graph and really get a good idea of how their shapes change. Now, because we only had 10,000 observations, if we would have picked more and more observations, we would see like method 1 and method 2 converge to the shape of method 3. So let's try that. Find my R. Find me later. I'm going to keep this one. Good. Okay. All right. I got a curly quote somewhere. Oh, there it is. Too much green, so I know something wasn't right. Okay, that looks good. Oh, I already have my ggplot statement there. Don't need it twice. Okay. So I'm going to run this. I'll run this. Okay, there's my data. Create a data frame. And then we have this function called stack. So basically, when we look at our variables, like these ideas, what we're trying to do is, well, let's look at data frame. Let's see what happens. Okay. So notice here we have data frame, and we have method 1, method 2, method 3. So what stack does is it tries to collapse the dimensions of your data. So it wants all the numerical values in one column and then the descriptors in the next column. So the second column, this first set of 10,000 observations, or here we've got 30 out of 16 to of 30 observations, you can see that these are all generated by method one. What Stack will do is it will take all those observations generated by method two and basically appends them like a row append, the way that we saw before, and puts all of the numerical data in one column. Then the second column is going to be the method column. So when we finish stacking this, we'll see the second column has all the methods in it. And so let's go ahead and do that. And so when we go back to DFS, you can see here's my method one data. And, then I went through my method two data and my method three. And so that makes it a little, because we are putting the data on the same graph, so we need to have the data stacked appropriately. So then we're going to create this factor, which is the column that has the method in it is going to become a factor because that's our categorical variable. And then we want to, create the density plots for each one of these. Okay. So one thing I should go back and point out is even though we said 10,000 random numbers, we only made our matrix have 30 rows. So that's why we didn't get 30,000 observations in either of the vectors. Because this says, well, I don't care how many rows how much data you generate. I'm only going to make the matrix hold like the first 30 observations each time. And hold on. Hey there.
Oh, good.
Something's wrong with your phone. Can you hear me?
Hello?
Oh, there you go. Now you sound normal.
What was it? Sound like a robot before?
Yeah, it came in kind of weird. I wasn't getting you.
Well, I just said good evening. Hope you're having a good day.
Oh, yeah, it's almost over. I'm still working, so.
Oh, yikes. You want me to call you back?
No. I'm recording a lecture. I'm leaving the country tomorrow, so I have to make sure
Yeah.
I'm headed to Korea.
Yikes. Have you ever been there before?
Never been there before. No.
Wow. How long are you going to be there?
About 4 or 5 days. I'm a keynote speaker for a conference. So they're flying me over and putting me up for a few days and let me see the city. And I only have to
be a pretty big deal for you to be a keynote speaker in Korea.
I know. It's like I only have to speak for like an hour and a half and they're flying me. I know they're flying me first class and everything. I was like, wow,
that is awesome. Good for you.
They must be really interested in what I have to say.
Yeah. Well, that makes you feel good, doesn't it?
Yeah, plus they're paying me. So I'm like, oh, yeah. That's even better. And I get money. Right. Yeah. Okay, cool. I like that.
Just make sure you don't end up in North Korea.
Oh, I won't end up in North Korea. Yeah. I'm sure I'll be okay.
Okay. Well, what time did you leave tomorrow?
My flight takes off at 8:25 in the morning.
Oh, geez. Okay.
Yeah.
Well, so I don't know. I have not talked to Warren. Has he contacted you today?
No, I did not hear from him.
Okay. He was having a day. Let's just say that. He had one of his best friends and our developer of a couple of our properties recently, just very, very recently passed away.
Oh, wow.
So we had some of that. So he told me. So.
Well, he probably won't be able to reach me tomorrow.
Right.
Yeah.
So yeah, I mean, he just wanted to talk to you. Trying to get some, at least some solace that everything is working, moving towards the same goal. It just takes. I mean, it's just we're the fastest growing city in the country, and they don't have enough people to do everything. So We're still waiting for the through the Grand Dunes for approval, and then it goes to the city for permitting. So, it should be in the next 2 weeks.
Yeah, I guess I guess that's what I didn't understand since, I thought I had already approved the plans.
To be able to get it to the city, because the city looks at it and says, all right, now how are you going to build this house and make sure all the requirements for the local construction codes.
Oh, okay.
Yeah. So yeah, unfortunately. So I mentioned to you that last time, or maybe in an email, that my last client that signed right after you, I'm sorry, before you, hers took 94 days from the day she signed the contract to where we could get them.
Right.
So it's longer than normal. Usually it's in the 60 to 70. But it's just, you cannot even put construction going on.
Yeah.
So it's just bananas, and they don't have enough people to paper just sit there and sit there. But we're still going to be, on time for your home, so that's not a problem. When you sign the contract to move in, we have very rarely missed our dates. If
So
we do, it's usually because it's a storm.
the 1 year from the contract signing.
Mm-hmm.
When did I sign? Did I sign in July?
I don't know. I'm not.
Because I closed in August.
Yeah, so probably June or July. Yeah.
Oh,
It
okay.
usually takes about 60 days, 45 to 60 days to close. So yeah, so you probably did that. So we'll get you on on your target. Very rarely miss that, and we very rarely go way under that. So
Yeah.
but I want you, as soon as you get back, I will make sure that that's all got some peace of mind.
Yeah.
But
So
it's the reason as many homes they do is they're constantly sending things in for engineering and approval because they don't, they're cookie cutter. They only build them one way.
right.
Or for custom, and so we can't do that, obviously.
Yeah.
So that's why, because people come in all the time to me and say, hey, well, how come they're building, this many at a time and this many at a time? Well, because they're just every single week, they just send 35 plans and then the next week they send 35 more plans. And, when you get the permit, you have a year from permit issue to start. So they can just let it sit there.
Right.
So it's a little different, and I know it's frustrating. And believe me, I'm not discounting your concern and your thoughts on it. But this is where we are. But trust me, you're going to be much happier in one of our homes than theirs.
Yeah. So what's going on?
Especially that Del Webb one up the street. So
yeah.
I've already heard nightmares about that.
Yeah. So where are you with the other units in the community?
So we've decided that we are just going to spec the other 4 lots out. We have 4 lots to be. And I have tried to, and I think I told you this, I have tried to talk to Boston doing that 6 months ago to at least get them going. Because nobody really wants to wait, not nobody, but you're not a nobody. A lot of people don't want to wait a year for a house. So I said, look, just build them, spec them out, because we've got a lot of competition around us right now that are popping up homes like mad. Right across the street, you got the Lennar neighborhood is going. They have 28 homes under construction right now.
Wow.
Only one sold, but 28 homes under construction at one time. So that's the difference between them and us. But they're also asking a ton of money. Sold one for $1.040 million.
Wow.
It's a garbage house. So it's going to raise the values. I just sold a house in a resale home, and it closed for 1.169. So
in the Cape.
Mm-hmm.
Yep. Which one was that? Was that the one with the pool and everything?
Yep. 8418.
Oh, it finally sold, huh?
Anyway, yes, it took a while. We had 57 showings.
Wow.
That's a lot of showings.
Yeah.
It just took the right person to get it, and some people thought it was, the price was too high. We had it appraised, and we're only $20,000 over the sales price. And we started higher than that because I figured, what, we'll cut this sucker. Somebody that just sees it and wants it. And funny thing is today I actually had 3 people that wanted to go see it. We haven't had 3 people see it in a day ever. So
Wow.
activity's starting to pick up a little bit. So I'm showing there's another house in the neighborhood on the market, and I'm showing a couple that saw that house, the under contract today. But we're going to go see that, and I would probably bet half my commission that they're going to buy that.
Hmm.
That's the one for $929 with a small pool in the back.
I just remember when I had kind of was it a kidney shaped pool or something?
Yeah, it is a kidney, and it's got a huge hot tub that falls into it. This other house is smaller and has a smaller pool, just 2 of them, and they're like, we can live with that.
Oh, I didn't realize.
That could be another option. Yeah, so we're starting to pop it a little bit, and so what we're going to do is we're going to do the 4 spec houses and just put them out all at one time. And I've designed them all. I already know everything that's going in and on them. I know the prices, and so it'll keep the values high. And yours is the one next to you is going to be the first one to start. That way, your house and their house, we're going to do those at the same time. You don't have to worry about moving in and waiting for your construction. So we'll do them both at the same time.
Oh, okay. So have they cleared the lot yet? Oh, okay.
By the time we don't really clear lots. We smooth them off a little bit. Then our crew comes in to dig your footers, and then they mess it all up.
I mean, they still have all that equipment sitting there, right?
It has still have that sea container where we keep all of our supplies. So yes, that'll be off. I mean, he can clean off that whole lot half a day.
Mm-hmm.
So as soon as we know it's at permitting, he'll go over there, and it's not quite in permitting yet. It's still at Grand Dunes.
What's the Grand Dunes?
Grand Dunes is the master, neighborhood that you're bought into.
Uh-huh. So where do they have an office that looks at the plans?
Which for some of their neighborhoods, for our neighborhood, we only have 5 plans.
Right.
But it's part of the bureaucracy. They have to have it approved, and then it goes to the city. So once we know it's at permitting, then Robert will go over there and clean off that lot, take that sea container out of there, and take the fence down, and those 2 lots will be ready to go.
All right.
Then the one next to it.
All right.
Your neighbor moved in next door with the ones that put up those walls down the side. And, he is loving it, and actually helped him move the table in today.
Which one is that?
It's the one on the left of you if you're looking at your house. The number 7.
Oh, I thought the builder lived there. No.
He's our developer. He bought the land. He puts the streets in, puts the lakes in, and we buy the lots from him.
Oh, so he doesn't live there.
Yeah, he now moved in full time.
Oh, okay. All right.
Yeah. He went through a divorce, and he didn't want to go too far from his old neighbor. He used to live across the street in the Dunes Club. And so he just wanted something smaller, and so it's good to have him in the neighborhood. He's probably, if not the number 1 developer in the Myrtle Beach area, he's the number 2. So he's really good at what he does, and a nice guy. So you'll enjoy that.
Cool.
And other than that, I just hope you have a really good time over there. That's going to be really interesting. It's nice to hear that.
I don't eat fish, so
yeah. Okay.
No, I don't eat that stuff. But yeah, we'll see. Let's so you said in about 2 weeks. You think before that?
That's what we're hoping. Yeah, everything right now is just let's just hope, because there's no control over it. If we call the engineer, or once it goes to the city, if you call the city and say, hey, when do you think it's going to be done? They're going to take it wherever it is in the file and move it right to the bottom.
So who's paying the monthly assessments? Are there monthly assessments yet for that lot?
Yeah, you should. Once you take ownership, you're actually responsible for that. You probably, when you signed and closed, they usually do a 3 or 4 month escrow. So they probably have already charged you for 3 or 4 months. And then because it takes that long for the HOA to get the information from the city that you now own the lot, and then they'll put it into their system, and then they'll send you an email with either a coupon book if you want it mailed to you, or you just will have electronically deducted from your account the HOA fee. So
Yeah.
obviously you haven't heard anything yet because you wouldn't ask you that question. So you should probably hear it very soon because, like I say, they usually take 3 or 4 months off.
Yeah.
They know the paperwork is done. So you've already paid for the first 3 or 4 months that you've owned.
Well, that's why I'm concerned because there's no activity and I'm paying for
Yes.
something that I'm not deriving a benefit from.
I know that's a rule in Grand Dunes is that they require that the homeowner own the home during construction because they would rather fight with you than me as the builder. Not me personally, but us the builder. So everywhere in Grand Dunes, anybody who ever builds a house, they have to buy the lot and close on it before the house starts. That's just a requirement, and not all neighborhoods do it, but most neighborhoods do it. Just because of lawsuits and things like that, they just don't want to have any issues. It's harder to go against a builder who's a corporation than just a single person. They might fight with a single person.
Wow, that makes it tough for me, right?
Well, I mean, everybody in Grand Dunes, all 3,700 homes has done it that way. So you're sort of in good company if you look at it that way. But I mean, we've never had an issue. Somebody go to court with us, so I don't think that's a problem.
No, I just want the house to get built. I'm just.
What the first thing was it? I know. I mean, you get anxious, you're justified. Justified to be anxious and concerned. Start paying $200 a month. But honestly, at the end of the day, because you've seen homes are all perfect. So you will have a perfect home. Can't wait to see that back wall, that triangle window.
Yeah. All right. Well, I will.
Now I will make sure. Wait for a few days and contact you. The early part of next week. And,
I won't be back. I won't be back. I don't get back until the 18th.
Okay. I thought you said 4 days.
Well, then I have to fly to Kansas City, give a presentation there.
I didn't know you're such a big deal. Look at that. Nice.
I didn't either. Apparently I am.
Well, take it.
Yeah.
Keep taking it. All right. Well, I will make sure. And if you get some time in between or something, just shoot me a note or a text and say, hey, I got the next day and just play over, and I'll have them call you just so you feel a little bit more comfortable that it's coming from the owner of the company.
All right. Sounds good.
All right. Well, you have a safe trip.
Thanks.
Have an exciting trip.
Thanks.
And yeah, I can't wait to hear all about it.
Yeah. Well, I got to make some plans to come down there anyway.
Oh yeah. Because once we get permit, I'm definitely going to need you down here because we got to go start making some selections.
Yeah.
So I don't know if you've been looking online and looking at different, color schemes and designs and things, but we'll make an appointment for you to go over to the flooring store. Probably get you over to the lighting store. We'll also get you to the cabinet store.
All right, sounds good.
You'll need a few days for that.
Yep.
All right.
All right. Well, I'll check in with you when I get back.
Please do, and have fun.
All right. Thanks. Take care.
Safe travels.
You too.
All
Bye.
right. Bye.
Okay, so let's take a look at the graph. Okay. And so there you have it. And so and this looks a little bit different from the one in the notes because we're using random numbers. What I want to do is I want to go back and increase the number of rows. So let's say I put in 10,000. Let's hope I don't blow up the matrix. 10,000, because you can see the shapes don't look really normal, and we are taking numbers from a normal distribution. So this will show that the more observations you have, the closer this thing starts to, the more this thing starts, the more these different graphs start to look like normal distributions. Okay, and so there you have it. So at 10,000, you can see they're all have normal distributions. They have the right shape, and you can see the means are exactly where they're supposed to be. So the first one had a 0 mean, and that's this method 1. The second one had a mean of 2, which is around here somewhere, because that's 2.5. So the mean of 2 is right here. And then the third one had a mean of 5, and you can see that's going straight through the middle. So there is some kind of a little bit jagged around the edges, but overall, all of the graphs have a normal shape. So you can see the number of observations really impacts the shape. If we don't have enough data, we're not going to really fill out the shape of the distribution. And if we were to up this to like 1,000,000 random draws, these distributions will look even better. But I just want to make sure you saw that. Okay. All right. So now we can facet and take a look at, and again, faceting allows us to add an extra dimension to our two-dimensional graph. So in the first case, we didn't facet, right? We just used the color variable in the aesthetic. And so now I can see drivetrain, the different distributions for the different drivetrains. And you can see front wheel looks very different from the four-wheel drive and the rear-wheel drive. The other thing we can say about the four-wheel drive is that it doesn't appear to have as much data as the other ones. So that too could be affecting why it's very similar to the rear-wheel drive. But even in practice, you know, front wheel and rear wheel and front and four-wheel tend to have similar performance. If we facet, we can get different graphs for each level and take a look at it that way. And we can still kind of see, you know, the shapes from the frequency polygon over to the histogram. We can correlate those different shapes because these in the frequency polygon, it's just we're just playing connect the dots with the midpoint of the height of each of these bars, and that's all there is to it, all we're doing. But again, we're using 3 dimensions to describe our data, and that's very helpful. A bar plot, you know, is just a raw count, and in this case, we don't really see, you know, the problem with this graph is that the names on the x-axis get a little overlap. They start to overlap, and while you can still read most of them, it's just not a pretty graph. But you can see you have a lot of Dodge cars, and this looks like Toyotas are in demand as well. So that gives you a sense for the dispersion over manufacturer of your data. So we can do things like summarize. We can look at unsummarized data, and we did this as well when we used the table function. And we can also summarize the data and create graphs out of that as well. So in this first case, here's our data. We have a data frame with like 3 different drugs, and here's the effect. We don't have the raw data that makes up each one of these effects, but we just have the aggregated. This is probably the average effect. And so we want to look at both bar plots, and here we use we have to use the option stat equal to identity because we're giving the function the height of each bar. And so that's what the effect is, and that's what this telling you. Otherwise, we saw, and when we had basic R, if you don't do that, if you don't give it this summary kind of command, even though it can't with this data, but you don't just want it giving you a bar for every data element. You want the graph to tell you a story about what's happening within each of your categories. So in the first case, we have our histograms. And one thing that's really important about histograms, and this really is from psychology, that when you don't start your histogram at 0, notice we have a 0 point here, it creates an illusion in the graph, and it kind of tricks the mind into thinking certain data elements are more important than others. And so that's why, one rule in creating histograms is to always include the 0 point. Now, a lot of people don't. And when you look in, I know USA Today, that newspaper, I don't even think it's around anymore, but they were kind of notorious for creating graphs where they didn't show the 0 point. And it gives you a misleading impression of the data. However, you don't have that problem if you're just going to plot the points. Okay. You can cut off the graph, because here you have each point really is the same, has the same amount of ink, and it doesn't create a distortion in the measure of each effect. It doesn't distort that. But if you were to cut off, in this block graph, like around 2 point, well, that's 2.5, so like 3 or 3.5, wherever that is, it could make drug A seem vastly inferior to drug B and drug C, when in fact it really isn't that much difference between those two. But you can see B is definitely the standout. The other type of data that we look at a lot is time series data. And you've seen time series data because you've seen the stock market. And so that data typically follows some kind of path. We study kind of like this randomness of the stock market all the time. There's been lots of books devoted on the randomness of the stock market, and hoping that it truly is random. There are some tests that can demonstrate that maybe it's not as random as we think it is. There's a book called A Random Walk Down Wall Street. If you ever have a chance to read that book, it's a pretty good book on this issue. But there are other calculations that actually show how these different graphs can be a little bit may not be as random as they seem, and there are metrics that you can apply to calculate that. So with this economics data, you can see we're looking at over the years from 1970 out to 2005, I guess, or a little, 2005. And so and you can see that the data, it seems to be increasing, and then it comes back down, and then it goes back again. And when you look at this data, you can tie this to what was going on in the world, or in the US, for example. Like, were we in a recession? So we saw, did the stock market crash? You probably have heard of some of these market crashes. There was one around just below around 2009 or so, and that had an impact for quite a while. So we economists like to study these trends. And so this first graph is the unemployment rate, and the second graph is the number of weeks unemployed. So again, as I said before, you really do have to understand the data, like what everything means, in order for you to really lend some interpretation to the results. So in this first graph, we graph by date the unemployment rate, and we used a geom line to see that relationship. And we did the same thing in the second graph, but now we have number of weeks unemployed versus as a function of date. And so in order to do that, we had to pull off the year function off the date. So we saw we stored that value in a variable called year, and then we created our graphs. Now in this case, now we're trying to look at all of this plotting like on the same graph, and so we're going to add a different kind of color, something called gray 50, to try to color the path based off of the year. So we've got the aesthetic, which is the year, and we're going to, every year is going to have a different color. And the line is also going to come from this gray scale, is going to come from this gray scale itself. And down here, this just tells us exactly what each of those two variables mean, which, you know, we start, I discussed that before we actually saw the definition. So really we have 1, 2, 3 lines of code that are going to generate the graph. And so here you can see, if we look at this, and basically what we did was we took this data and we collapsed the year, and then we analyzed it based off of the relationship between number of weeks unemployed and the unemployment rate, because that also has a relationship. And so this kind of looks like a crazy graph, right? If things seem to be falling back on each other, it's not really all that interesting. We can't figure out where one year begins and another one ends. And that's sort of a limitation of this graph. Although if we knew that, we might be able to find some interesting information. The most important thing is that the line that is connecting these dots is a path. It's a path that is chronological. So it's not like we took a graph and tried to connect all the dots from left to right. We took basically this graph and the two relationships, these two relationships together, and we said, well, let's do a graph that plots the coordinate pairs from each of these two graphs. And in that way, we collapse the year. So the first point here is we take as our, let's see, what did they take it as? Okay, we took the 1 point here, the unemployment rate, that was our X, and then we picked off a point from this graph, the number of weeks unemployed, that was our Y, and then we plotted it, okay? And then we wanted to keep track of what year each point was from, so we strung all those points together based off of their year. And that's why it looks like you have a line that folds, goes back this way, it goes up, then it comes back, and you know, which is not the way you would typically connect dots in a graph. But now we're following the points according to, you know, what year they are. So the year becomes our path, and we're calculating the points, those coordinate pairs along that path. So what's really nice is when we put in the color, then this graph starts to make more sense. So here, when we say our color, right, this is no color, this is nothing, right? We didn't do anything here. You don't see any color being used as an aesthetic. But when we start to use color as an aesthetic, right, here we have the year as the year of the date. Then now we can see the different years kind of sharing the same graph, and they're lumped on top of one another. So we can see like the darker regions the darker points are from 1970, and you can see that relationship has, number of weeks unemployed versus unemployment rate, pretty low. And it makes sense because if you have a lot of people that are unemployed, that must mean the unemployment rate is high. And if we look at now 2010, this much lighter color blue, we see those points are elevated, much higher in the graph because again, it also had an unemployment rate of 0.03. There was some weeks unemployed around 12.5 weeks unemployed. So this way, again, we get to add a third dimension to the graph, and we still look at our underlying relationships between these two, but now we can look at them, this relationship between number of weeks unemployed and the unemployment rate along the dimension of year. And we can see it right here. We can't really see it. We don't know what the years are, but if we knew which years these points belong to, then we could make more sense of the graph. And that's what we did here. So notice when we pick a color, we say, here's our path. We want it to be gray 50. And basically this gray 50 is this continuum of colors. And then what variable are we going to use? Well, we're going to use year. If there's some other variable in the data set, you could try that too, but this makes sense because we started out looking at these two graphs separately by year. Now we want to collapse year and look at the relationship, but we still want to know which year each of these points belong to, because that's also going to tell me that I can go back in history and say, hey, what was going on? What in the world that caused, or in the US that caused these numbers to look the way that they look. So that's a pretty powerful thing to be able to do. So you're going to take the auto claims data set, and you're going to study the claims in the first quarter of 2015 as a time series. You're trying to analyze the effect of month on the time series. So just like we were trying to understand the effect of year, now you're going to understand the effect of month. And you're going to create a path plot with points and color the data for each month a different color. So we already know how to do that. And then we're going to analyze total claim amount as a function of policy annual premium. And these are two fields. So we have our Y variable, and here's our X variable. And so we plot all those points, but we want to know which points belong to January, which points belong to February, March, April, May, June, July, etc. And that's where the color parameter comes in. And this was a real data set that I downloaded from the Kaggle website. So we can modify our axes in graphs, and that's really not so impressive, but we can change what numbers are included on the graph. We can change our colors of the point, and that's what this alpha function does. It's like the transparency function. It says, I want my dots to be 1/3 transparent. And again, the helpful thing about using this transparency parameter is that when you have one dot, it's pretty clear, but when you start to get over plotting, then that area gets darker. So the darker the dots, that means the more dots that are over plotted in that particular location. So these look like one dots here, but then this one looks like I have two dots plotted on top of each other. And the darker these dots get, the more that you have dots stacked on top of each other. So with this one, what we're doing in this graph is we're adding the labels. XLab stands for X-axis label, city driving, and Y-Labs stands for the Y-axis label, which is highway driving. And you can also remove those labels just by using the null argument. Again, we can, this one shows you how to modify XLim right? Lim means to limit what you put on the x-axis, and x-axis, and lim means to limit what you put on the y-axis. So for x-lim, I only want to see front wheel cars and rear wheel cars. And so you can see we went from showing all three to limiting it to just front wheel and rear wheel. And then on the next one, we said, well, now I want to limit my X limbs from, going just 20 to 30, right? I just want to see the range from 20 to 30. And so you can see we have that as well. And then in this last graph, we did some jittering, and we changed the width a little bit of the jittering to like 0.25. We didn't want it to jitter. We didn't want it to spread out too much. And that's what the width argument does. And we're moving the values. And so here we go from Y limit is from whatever, if you have NAs up to 30. And this basically says that you're going to set values outside to the range to NA. So, that's fine. That would, that would include that. So the other thing we can do is we can store a whole graph object in a variable. And we've seen this graph before, so I don't need to go through the line of code in this graph. We've seen it before. And we can store it in a variable, and then we can print it. Now, the ability to store graphs in variables allows you to do some, you can print graphs in a loop. There's lots of things you can do once you can store objects in variables. But then you just, if you want to print it, then you can see exactly what the graph is. Okay, so the last section of this lecture involves the diamonds data set. And diamonds, you said that they're a girl's best friend. We're going to look at how we value diamonds. And so the structure of a diamond, we have like 4 different measures of a diamond. We have like the table width, and then its outside width. And then we have the Z depth, which is from the table down, and then the total table height or the depth. It goes from the top facet, the top flat surface, down to the bottom of the diamond. And so these measures become important in determining how valuable your diamond is, in addition to the 4 C's that we always talk about with diamonds. But these dimensions actually influence how well, influence the 4 C's. Let me put it that way. So we've got, how large the diamond is, that's our carat. How well the stone is cut, there's the cut. Then we have the color, and then the clarity of the diamond. If we want to look at a diamond's table percentage, well, this table percentage is calculated by dividing the width of the table by the overall width of the diamond, as illustrated here. And, for different diamond shapes, these percentages vary in terms of what's ideal. But for a round diamond, anything between 54 to 60% is considered ideal. But for an emerald cut, that percentage, it goes to 66 to 72. So that's another way for the other cuts, they have similar percentages, but we don't talk about them here. But there's another way to kind of get a sense for the quality of your diamond is by, asking the jeweler, what is the table percentage for this diamond? He'll probably be shocked that you actually know that. Then we have the depth. So the depth of a diamond, could also be called the height. And, it's the distance from the type of the cullet, which is from the table to the cullet, this pointed thing at the bottom is called the cullet. And Jewelers also grade diamonds based off of this depth. And so the percentage is going to dictate like how well light bounces off the different facets inside the diamond. The ideal depth is also going to vary based off of the shape. And so you want to look for a diamond that allows a lot of light to bounce around. That's why people, look for very sparkly diamonds, because very sparkly diamonds are more valuable than diamonds that don't sparkle as much. So this is the diamonds data set, and I just did a quick plot using base graphics, and you can see when I plot diamond carats on the x-axis and price on the y-axis, I get a pretty plain, boring plot. But if I use qplot, which is part of the ggplot package, I do get a much interesting plot. However, I don't want to sound like a snob, because I use plot a lot if I just want to get a sense. It doesn't have to be pretty for me to understand whether or not the data looks good. I don't need all these pretty details. So, but if you're creating a graph that's presentation quality, then you might want to use the qplot version of the graph. But just remember that just using the graphics in base R, you can quickly get to understand your data. You don't have to load any packages. You don't need the library command. You can just get a quick look at your data and then decide, if you have any issues with it. And that's just part of the analysis. So for this homework example, you're going to display the first 6 rows of the data set. You know how to do that. You're going to display the last 6. You're going to look at the summary, the structure, the dimensions, and then you're going to plot a basic histogram of the prices of the data set. But now you're going to be using ggplot for that, right? So you should get a nice, pretty graph like that. Then you're going to replot this with a bandwidth of 500, and you're going to add some labels to your graph, like diamond price distribution, your X label, your Y label. And then in the next graph, you're going to create, again, using a bandwidth of 100, pretty much the same graph, but this time you're going to facet the graphs based off of cut. So you're going to get a different frequency distribution or a different histogram based on the different cuts that are in the data set. So that you'll look at your cut variable and see what are the levels in that data set. Then you want to calculate the mean of the prices, the median, the max, the minimum. These are all things you know how to do. You want to get a count of all those that have a cut equal to fair, then good, very good, ideal. And then you want to create a contingency table. So you know how to do that as well. Then you want to answer these questions, like how many of the diamonds cost less than or equal to 500, less than or equal to 250, and then how many are at least 15,000. And display the records with the highest price diamond, display the records with the lowest price diamonds, and then display records for which cut equals fair. Calculate the median prices for each cut of diamonds, and then create a box plot of diamond prices based on cut. Again, all of this, you have all the code you need to do that assignment. And then finally, you're going to calculate the price range for the middle 50% of the diamonds with color D, and then for the middle 50 of diamonds with color J, and then you're going to tell me what the IQR is for color D diamonds, and then what it is for color J diamonds. So you can do all of this. You've got your quantile functions. You know how to do all of this, this work. And that takes us to the end of topic 1, part 3. And so again, I regret that I can't be with you in class on Friday, but I hope this video makes you feel like I am in class with you on Friday. And you don't have to watch it on Friday. You can watch it whenever you want to, but just take note of when the homework is due. And then I'll be back the following Friday and we can pick up where we left off. We'll be starting topic 1, part 4. And I think we'll talk, I think a quiz may be coming up as well. So we'll talk about that too. So anyway, I will see you when I get back.